Okay, hello guys. So my name is Dmitry. I am CTO and co-founder of Fluent Labs. Today I want to talk about why the best VMs are blended. So let's start with the definition of blended execution of Fluent serves. What is it? So blended execution is the concept that is used to merge different execution environments and different VMs in one place. So you can run contracts inside Fluent using EVM, WebAssembly, for example, SVM contracts. You can develop it using different languages like Solidity, Rust, any language you want. That's like the basic concept of blended execution. But how blended execution works? So to make it possible, we have so-called blended VM. Blended VM is not a multi-VM. There is a huge difference between blended VM and multi-VM. Because in blended VM you have multiple instruction set architectures, and you execute different instruction according to the type of your smart contract, and you store information about different smart contracts inside your state. In blended VM, it's not the case. In blended VM, we store everything using only one representation, using only one VM. And we translate all virtual machine, all languages into one intermediate representation. So let's put several constraints into blended VM, how it should work to achieve all these requirements. The first one, as I mentioned before, blended VM use only one intermediate representation language to represent all contracts. Also, it must have stateless machine without access to storage or any external devices. So you cannot directly access information about, for example, storage inside blockchain. You need to use a special scheme. The scheme we call interruption system. So interruption system is the way how developers can interact with the external storage and with other smart contracts. I want to talk a bit, I will return to interrupted system a bit later. The first blended VM that Fluent delivers is RWASP AR, or RWASP Intermediate Representation. RWASP here stands for Reduced WebAssembly. RWASP is 100% compatible WebAssembly binary intermediate representation. That's super important because RWASP passes all official WebAssembly testing suite, and all functions, all bytecode you can create using WebAssembly language, you can also create using RWASP language. And it makes possible to create a compiler from WebAssembly into RWASP and prove exactly the same transitions you have for WebAssembly and for RWASP. What else do we know about RWASP? RWASP has much better ISA that is fully compatible with WebAssembly, but it is delisped, so we eliminate all tree structures and replace it more flattened structure that is much easier to prove and more efficient to prove. And also it is EIP 3540 friendly. That just makes more friendly with the upcoming Prague fork. Also RWASP means 100% WebAssembly transition equivalence. So for all transitions, for all ZK transitions you calculate for WebAssembly are similar for reduced WebAssembly. We eliminate interpretation overhead. So all this is required to achieve this, to solve this problem. So by eliminating implementation overhead, we can execute all smart contracts, all state transition functions in the same execution level. There is no need to create an interpreter that interprets operations. You just create a contract and it executes on the same level as state transition function. And by using compiler, we can verify correctness of the binary structure. We also can prove that there is no out of bounds, and we can eliminate additional bound checks because all bytecode is already verified and generated using a verified compiler. Also, one very important thing about our RWASP AR, it is used to represent all smart contracts, all applications developers deploy, and also it is used to represent the entire state transition function. So the full state transition function is represented using only one binary language. What's about interruption system we use? So let's assume you have two applications that want to interact with each other. Your root state transition function executes the transaction A, and during the execution, it calls transaction B. So since all contracts are stateless, it's impossible to do a direct call from application A to application B. And instead, we just return execution back to the state transition function. It executes function B and then returns result to the application A. That's how we achieve interaction and also access to storage, to transient storage, to pre-images, to contracts for deployments for these applications. So all EVM-compatible functionality can be achieved by using this scheme. Then, what benefits do we gain by using blended VM? So there are four main. The first one is much faster proving. So we have more friendly SA, we have less instructions, we can replace uncomfortable instructions. Some instructions are very expensive to prove. For example, pop count, there is no need to implement pop count, and you can just, during the compilation process, replace it with precompiles. Also, we have significantly less trace size because we eliminate the interpretation overhead. Also, all blended VMs has native parallelization, and it's not an optimistic parallelization, it's active parallelization. So there is no need to enable mandatory access lists, and it helps to keep 100% compatibility, for example, with Ethereum transactions. And any type of transactions you want to run on Fluent, no matter how it's constructed, is it Solana transaction, Ethereum transaction, they all will have native parallelization. Then, blended execution serves delayed execution. Using delayed execution, you can split your transaction into multiple transactions, and it happens automatically and smoothly for developers. So you just create a transaction, and it automatically decides, according to different policies, when to split a transaction into multiple blocks. For example, you have a block size 10 million gas, but by using delayed execution, you can execute transaction for 100 million gas. It will be executed in 10 blocks. And there are different policies that can be used to delay the execution of a transaction. Then, Blend VM brings infinite expressivity. It means that by creating new compilers, by adding new runtime support, you can dynamically expand the system without even doing fork, because you can just upgrade, for example, hashes of your compilers. You can outsource the compilers to ZK providers. You can create the compilation proof from different execution environments from different language into our WASM representation, and you can prove everything and expand the system. Faster proving. What does it mean and how it works? So, as I mentioned before, our WASM is WebAssembly, but better. It means that in WebAssembly, you can do the following. For example, you have WebAssembly in your browser. You can execute your WebAssembly natively inside your browser. You can use any well-known ahead-of-time compilers, just-in-time compilers. There are a lot of tool set for WebAssembly already, but there is no need to create a transition proof for WebAssembly because it's very expensive. Instead, you can create transition proof using RWAS, and it helps to optimize the key proving significantly. So let's compare the trace size difference comparing to interpreted version of WASM using RISC-V versus RWAS. So for the smallest hello world application in RISC-V plus WASM, that's actually SP1, you need to spend almost 500,000 instructions to prove the transition of your application. Using RWAS, you need to prove only 37 instructions. For key check functions, 1.8 million versus 20,000 instructions. The most complicated test is for SEC256K1 verification. In SP1, it takes 100 million instructions, but in RWASM, it takes 3.4 million instructions. Of course, this test shows only the difference in the trace execution, and there are a lot of additional overheads that can appear by doing SEC256 recovery, etc. But that's the performance increase comparing to the size of the trace you need to prove. So by mitigating the overhead for signature verification, you can optimize these numbers and achieve this result. So what about active parallelization? How does it work? So Fluent doesn't use passive parallelization, so it's not a block STM. It is active parallelization, but active parallelization requires to have mandatory access lists. For example, how it works in Solana. For Fluent, it's not required. Fluent can do active parallelization without mandatory access list and keep full compatibility with EVM structures. Because if in Ethereum, if you make all mandatory access lists, if you make all access lists mandatory, then several contracts won't work anymore for you. And you need to make sure that developers are aware of this. So by using Fluent non-mandatory access list parallelization, you solve the problem because you keep full compatibility with EVM. So how it works? As I mentioned before, we use an interruption system to interact between two synchronized states inside your application. So how WebAssembly contract looks like? You load some state, you do some heavy, intense computations, and then you upgrade the state. According to this, we can in the beginning of the execution, we can synchronize all states and just run all transactions in parallel, because we know that if the collision happens theoretically, contract all the time notify you by doing interruption. So we can create, like for example, a batch of 3 transactions we can execute in parallel, and we execute them from left to right by taking one transaction and synchronize them once we have the interruption. It is exactly the same concept that is used, for example, in your personal computer, where you have a conveyor that executes all your different cores, executes your bytecode, and when you need to access some resources, like kernel resources, like file system resources, you use interruptions to interrupt the execution of your application and access these resources. And during interruption, other transaction can be executed, because right now it waits for some shared resources. And you can, for example, if TX1 executes and requires for some storage resources, you can request the resources, and in parallel you can start working on TX4 and TX5, TX6, and etc. until you achieve the final result. There is one potential side effect that can be caused because of this model. If one of the transactions is extremely big, it can hold the entire execution loop, and other transactions will have to wait for the first transaction if it has a very intense computations. It can be solved by adding yielding according to gas policy, where we forcibly cause fake interruptions in the contract that according to gas policy. So once you achieve, for example, 1 million gas computations, you're forcibly interrupted with no operation. It's required to just to reschedule, to upgrade the execution pool, and to align all transactions with the same size. Then, delayed execution. So the yielding I mentioned before is implemented using delayed execution. Delayed execution can be configured according to 3 different policies. According to your gas policies, according to the block number, and external messaging. So gas policy is quite obvious. You can just use gas. For example, once you achieve 10 million gas, 1 million gas, you can reschedule your computation for later execution, because it's very expensive. You can ask, okay, I want to execute my transaction, but once I spend, for example, 1 Ethereum execution, I want to postpone the execution like to the next block. It is important because if you have local fee markets, you don't want your transaction to be interrupted, and you don't want to align execution of a transaction in a specific percentage of the gas limit. So you can just configure a transaction to be automatically interrupted in case if you don't satisfy the requirements of the block execution policy. Also, you can do delaying according to the block number. You can ask, here's the example of such application. You can create a contract that has infinite loop inside and just sleep for n blocks. For example, execute all these high computations only once per 10 blocks, or for example, each block. Using this policy, you can create something like cron jobs. You can get timers. You can execute your very small transaction in every block to track modifications, for example, inside LP pool, and do fast rates, etc. Also, by using base fee plus tips, you can manage the threshold of your gas that can be spent for the execution. And also, the last one is external messaging. Your application can request external information from other sources. For example, you can request information from an AI agent that can also be verifiable on chain, since this process may block the execution of your application, and you can just send a synchronous message and continue execution, for example, 10 blocks after, once you have the response to this message. Of course, there are several potential bottlenecks, and the delayed execution policy will be limited, for example, with the maximum possible lifetime, let's say not longer than 100 blocks, because in case of the node restart, you'll need to reconstruct the entire state and prove all memory and stack transitions. So there will be some hard limit, but I think it opened a lot of doors for developers to create new types of applications that are more Web2 friendly. So we are not limited with size of transaction. You're not limited with block gas limit anymore. You can do asynchronous request to third-party resources without any limitations, and etc. So the infinite expressivity. As I mentioned before, by bringing infinite expressivity, Fluent can support any language we want. There is no need to support a concrete language. Instead, we support virtual machines and execution environments. So right now, we support EVM and WebAssembly. SVM is still work in progress. We're going to deliver it a bit later. And any VM that developers can create, they can run it, for example, inside Fluent. They can create compiler, or they can compile it to WebAssembly and run inside. If they create compiler, they gain the maximum blended benefits, because all the application can be executed natively using WebAssembly, using RWASM, sorry. So that's about Fluent, the first blended execution network. Yes?
So I have two questions. On the first one, is the instruction set is a custom one on your own that you developed, or is it something like that's been already common in the open source world or something?
So our instruction set right now is inspired from WASME. It's a fork of WASME with modified instruction set.
Yeah.
We adjust instruction set for more ZK friendliness and to support our functionality. But we're eliminating these dependencies right now, and we're creating our instruction set. But our instruction set, our WASP instruction set, is inspired originally from WebAssembly. It's very similar to WebAssembly instruction set. We only eliminate several instructions that are not efficient for proving, and we replace them with some like snippets, precompiles, and etc.
Okay, makes sense. And also, I don't know the specifics. I also joined a bit later, but so the way I understand is like you're basically converting all these into RWASM logic and then executing from there all these
Yeah.
VMs. During the conversion phase of these specific, EVM to RWASM and WebAssembly to RWASM and etc. Let's say one of the VMs is not formally verified, and there's a sort of a bug or stuff like that in the own system itself. Let's say on the EVM side.
Yeah.
Does it affect your end if you want to, update a bug or something like that? How would you?
Oh, do you mean during the compilation process?
Yeah, both.
Yeah. The compilation process is fully removed from the virtual machine and from execution environment. It works with raw instructions. It works with raw binary data. So since if there is no bugs inside EVM bytecode, inside the bytecode structure, then it will work. Of course, we can upgrade our compilers by changing the hash of the commitment, for example. And but right now we have this. We have our compilers embedded inside Fluent, and during the deployment, we decide what compiler to choose. But we are going to eliminate it from mainnet release, because we are going to create like a computation marketplace where you can outsource compilation of your application. And if you want to deploy, for example, EVM app, you just ask external provider to compute the ZK proof for your application, and it deploys your application for you with ZK proof. So technically, inside Fluent, there is no need to support any VM at all. We can support only RWASM and only our state transition function. And the rest functionality can be achieved by using external ZK providers who can compute the compilation proof for us.
Yeah, the reason I ask is, like, it's not similar at all, but let's say you're trying to do something like evolution where you have two different DAs, and then in that case, if one of the DAs has a bug, then it becomes extremely complex, and that kind of reminded me, like, there are several factors that you have during the compiling the WASM stuff.
Yeah.
So I just wonder, like, let's say on the EVM compiler, there's a bug, and what are the steps to fix it and kind of stuff? Like, does it really break the system, or like, is it just a simple upgrade that you can?
It's partially break the system. Of course, you can do an upgrading, and you can upgrade the state. So of course, like if something like this happens, if that's like everyone in trouble, because if you have a bug inside, for example, EVM interpreter, that's the same. Like you need to upgrade the node to fix this. Exactly. So of course, all these compilers must pass a very strict audition to make sure that the compilation process is smooth. Also, one of the biggest requirements on our WASP that it's fully trusted and it has access to. It doesn't do any bound checks inside. Because it means that, for example, according to our WASP requirements, you cannot go out of the stack. You don't have stack overflow, stack underflow. And during the compilation of application, developer of compiler must be aware of this and make sure it won't happen in compiled application. That's right. Yes?
For long-lived transactions, say the one with some delay, and then it runs some logic, and then it might delay even longer, how long can they go?
Yeah, so the problem, the challenge here that nodes, validators must know, but must keep information about all delayed transaction and keep it for the longest period of time. Because in worst case scenario, you can execute, for example, your delayed transaction longs for 100 blocks. It means that if your node goes down, if it crashes, you need to roll back your block history for 100 blocks. If you expand this limit up to 1,000 blocks, then you need to roll back for 1,000 blocks, of course. So we just need to find a suitable amount of blocks nodes are ready to revert to reconstruct the state. Actually, it's not a reversal. They just need to reproduce the state to make to
Re-execute.
just re-execute only these delayed transactions. So of course we'll add some hard limit that limits validators from being dosed from malicious executors who create a lot of super heavy intense contracts and cause potentially crash of node. I don't know how it's possible, but of course we're going to add protection against this attack.
Because I was curious, like how many of these long-lived transactions can there be?
Yeah, of course. Since we're going to implement a local fee market, we're going to limit number of these transactions. They probably will be managed using auction, and only transactions with the best price will be included until it's normalized. Because otherwise, this transaction can fit the entire block, and normal transactions won't be able to be executed inside. Yeah, thank you.